This is the pre-lab video for kinetics of bleaching food dye. Our objective in this lab is to determine the rate law for a chlorine bleaching process, as well as what the activation energy is for that reaction. So what are we reacting? We are combining bleach with a food coloring or a dye, and this chlorine bleach uses the hypochlorite ion as an oxidant in a redox reaction, and it will oxidize stain. We're calling it stain molecules. It's really our dye molecules, and it renders them colorless. In part 1, you will measure the absorbance versus time for two concentrations of bleach, and the absorbance is proportional to the amount of dye in solution, which of course will be continually decreasing over time. And you'll perform both of these reactions at room temperature, and you need to record what that temperature is. The procedure you'll be using is to measure out your dye solution and your bleach solution into separate clean containers, and not mix those solutions until you're ready to perform your reaction and ready to measure your absorbance on the spectrophotometer. The burettes in the hood will hold dye as well as the two different concentrations of bleach. You need to measure out 5 milliliters as accurately as you can using the graduations on the burette. When you have all your solutions, you have your temperature, you're ready to perform your reaction, you have your spectrophotometer in front of you, you need to zero your spectrophotometer using a cuvette of purified water. And you need to make sure that you insert your cuvette properly into the spectrophotometer. The beam of light travels from left to right, so it's in the side-to-side orientation. And if you look at your cuvette, some of them have a cloudy direction and a clear direction, and the clear direction, when you're looking from the side, needs to go from right to left, so that path of the light beam can travel through in that direction. So you zero your spectrophotometer, and then you're ready to go. Take the blank out of the spec, and you're ready to mix your solutions. Just pour one into the other, and then pour it into the cuvette, wipe the sides with a Chem wipe, and gently place it into the spectrophotometer. Start reading absorbance and time data as quickly as possible, and then at the time intervals that you need to perform, and I'll go over that in the next slide. So here's some example data. You'll need 4 tables of data before you leave lab. 2 are for part 1 and 2 are for part 2. So the top 2 here are for part 1. They're both performed at room temperature. Now I have 21.4 here. Your temperature will be different. But you do need to record, if you're using a thermometer, you need to estimate that last digit. And the temperature data is important in this lab. You want to record this as accurately as possible, so make sure you estimate the last number. So you will be recording time and absorbance throughout the course of the reaction. In part 1, you will need to record the absorbance until it's less than 0.2 units. So this may go on quite a ways here, much past 35 seconds. But this 9 seconds represents, okay, this is as quickly as I could put it into the spectrophotometer, and I started reading. And then for the lower concentration of bleach, you'll be recording every about 10 seconds is fine. So then you will repeat the reaction using the larger concentration of bleach. And again, keep recording until it's less than 0.2 units. In part 2, you will repeat the reaction, although this time you will only use the lower concentration of bleach, and you'll do 2 trials at 2 different temperatures. So you'll have an ice bath with your solutions in an ice bath, record the temperature. Theoretically, it should be 0, but our thermometers are not necessarily calibrated, so your ice bath could potentially be, greater than 0 or less than 0, but you need to record the temperature and make sure that you use the same thermometer for all of your trials. So record the temperature that your thermometer reads. And again, you're going to be recording time versus absorbance. It's really important that you get the reaction into the spectrophotometer as quickly as possible, because the rate that you are going to be determining using the other 2 temperatures is the initial rate. So you only need to record You don't have to record all the way until less than 0.2 absorbance units. You just have to record the first, say, 20 to 30 seconds, but you need to have multiple points within that 30 seconds. So if you can get 4 data points or 5 data points, that would be fantastic, but you need to get them quickly. And you will repeat this with solutions that were kept in a hot water bath. You'll use your Bunsen burner to warm up water in a beaker, get your solutions into test tubes, into that beaker, record the temperature of the water in which you remove the solutions and start your reaction. And that should be about 40 degrees. Your hot water bath will heat up quite quickly with the Bunsen burner, so be careful not to go way beyond 40, and then you'll have to wait for your solutions to cool. The following is a link to a video that will help teach you how to make plots in Excel, and it's very important in this lab that you are able to do this because you have to make several plots for these calculations. Speaking of calculations, for part 1, our purpose here is to determine this rate law. So we have this format for our rate law because we have 2 reactants, our bleach and our dye. So these are representing our orders, and of course we need K. So we need a value for K, we need a value for X and Y. Throughout the reactions, the concentrations of bleach are such that the concentration of bleach is much more than the concentration of dye. So when these two react, the bleach concentration really remains constant. It does get consumed, but comparatively to this dye concentration, it's virtually constant. So if you assume that the bleach remains constant, then K is a constant and the bleach concentration is a constant. So this whole piece of this term then we can say is a new constant that we're just going to call K prime. So if K prime is K times the bleach concentration raised to its order, then we can rewrite the rate law with a new constant. So K prime now times dye raised to its order. This is now a single reactant mechanism here. So this new rate law contains only a single changing species, so now we can use the graphical method to determine what the order is with respect to dye. So for part 1, you will need to make 6 Excel plots. 3 for the lower bleach concentration and 3 for the higher bleach concentrations. You will plot absorbance versus time, the natural log of absorbance versus time, and 1 over the absorbance versus time for each. Whichever one is linear will tell you the order with respect to the dye, which is Y. You will attach the linear plot for both concentrations to your report. Make sure that you have an equation for the trend line for the linear plots, and the absolute value of that slope will be the value of K prime. Here's our equation for K prime. K prime equals K times bleach concentration raised to its order. Assuming that that order is 1, you can solve for K. So our absolute value of our slope is K prime. That number will go here. Solve for K, and our bleach concentration, depending on which trial you ran for that slope, you will enter that there and assume that X is 1. You'll also attach the absorbance versus time graphs to compare them for does the bleach concentration have an effect. We're telling you that it's 1, okay? So we're telling you that it does have an effect, but you should be able to look at the absorbance versus time graphs and look at those slopes and look at the progression of the reaction and say, you know, circle the areas on the graph and say, yes, there is an effect because, and then explain it, how you can figure that out from the graphs and attach those to your report. So now you have the value for X, which we told you is 1. You have the value for Y, which you determined based on which graph was linear, and you just solved for K. Now you can write your rate law, and you're done with part 1. You need 3 Excel plots for part 2. 2 of them are for both the high and low temperature trials. You need to make whichever plot was linear. It might be absorbance versus time, it might be log of absorbance versus time, it might be 1 over absorbance versus time. Whichever one was linear in part 1, that's what you'll plot in part 2 for both the other trials the high and the low temperature. And you will put a trend line, you will request the equation for that trend line, and the slope will help you find K again. Okay, so you'll do the same exact thing, find K prime from the slope, and then solve for K for the other two plots. Now you have three temperatures with the lower concentration of bleach reaction. 0 or close to 0 ice water bath, room temperature, and the warm water bath. So you have three different Ks that you solve from K prime. You will take the log of those Ks, so you have 3 log of Ks versus 1 over the temperature in Kelvin, and you will plot log of K versus 1 over temperature, and you'll get a 3-point plot for each of these three temperatures. Again, you will display an equation of the trend line. This should be linear. Display the equation of the trend line, and the slope now will be negative activation energy over R, where R is 8.314 joules per Kelvin mole. Solve for the activation energy. So you'll get your equation for your trend line, the slope, so y equals mx plus b, the m is the slope, that number is the activation energy, negative, over R. Solve for activation energy. In your conclusion, be sure to include your rate law with K, the value of K, not just the letter K, with its correct units, the value of the activation energy, and include sources of error. And this concludes this video.